Okay, folks, so today is this lesson. You are going to come back to me for a little bit of live at about 9:40. I'd like everyone to log on to Zoom. Today, before we get to that point, we are going to talk about what it means to be sigma or pi in terms of describing bonding. So we left it the last day at dot and cross. So we're roughly, it's page 145. And you have this representation of ethene, the bonding in ethene. So how would we now describing the bonding in there? So what is the ways we can describe this double bond? So I've just given it away, haven't I? So because we have this CC in here, it is a double bond. In terms of how many shared pairs of electrons, you now know that there should be two shared pairs in here of electrons. And we talked the last day in terms of describing the carbon-carbon bonding. It is described as having one sigma bond and one pi bond. And we're going to go into detail today about what it is that these things look like. So before we get in there, we are going to talk about carbon in terms of the new electron configuration. So carbon is 1s2, 2s2, 2p2. And it's going to be I wrote 6, 2p2. Hydrogen is just 1s1. And we now know from our dot and cross for carbon that there must be dot cross being shared here, like so, between these two carbons. And we now know that there is shared with a H here, shared with a H here, shared with a H here, and shared with a H here. So, and it is going to be the outer energy level electrons that are involved. So we know that for carbon it is going to be this S, and we know up here that it is going to be S's and P's. And we know in terms of the shapes of our orbital that the S orbital is spherical in shape. Remember, it's not circular because it's three-dimensional in space. And we know that P is dumbbell shaped. So in Leaving Cert Chemistry, we don't go into what's called molecular hybridization at all. We keep it very, very simple. But essentially this is a model. And what this is showing you is, and you have these pictures in your book, is that this is showing where the electrons are being shared between atoms. So these white is shared, there's electrons being shared, and these green up here, they mean something. So the first thing that we're going to say is these little black dots that were here and here, these are our carbon atoms. So if our carbons are here, it must mean that our H's are out at the end of these guys, of these white. So this is where the dot and the cross are orbiting, that are being shared between each carbon and each hydrogen. So these are the sigma bonds. Okay, so if we were drawing them, we just put in lines, but now we're showing the three-dimensional space that the shared pair of electrons are filling. So these are sigma bonds. They are the ones that go between atoms. So sigma is always the first type of bond that's formed between two different elements. And we're drawing them in here as lines. So in your picture on the bottom of page 145, the bonds between atoms are drawn as lines, and these are your sigma bonds. So this is the Greek letter for sigma. Here then, these are pi bonds. I will go into explaining what these are. So what happens is, this is our carbon. There's a sigma bond here already, and what we have are p orbitals that are on each carbon, and what those p orbitals do is they actually bend towards each other like this. And when they do that, then the electrons can reside in that space. So this is the sigma bond again here. And now what's after happening is we now have a bond that looks like this above and below the plane of the sigma bond. So that is what the pi bond is, and we draw them above and below the plane of the atoms. Okay, so these white down here are our sigma. So if you go over to the top of page 146, these are our white and our green here are our pi bonds. Now you won't ever have to draw the diagram, but what you will have to do is be able to describe what sigma bonds are. So sigma go in straight lines, so this is an S and an S in my head, and the description of them is that they're head-on overlap of orbitals, and I'm not defining what type. Is it an S or a P? It's actually a mix, but we're not going to go into that. So sigma bonds are head-on overlap of orbitals, and now the electrons are going to be in this shared space. So this is a dot and a cross, this is a dot and a cross, dot and a cross, dot and a cross, and up here in the green is where the other dot and cross, those electrons can reside. It's above and below the plane of the atoms. So sigma bonds are head-on overlap of orbitals, and the pi bonds are kind of parallel to your sigma, and they are described as being sideways overlap of p orbitals. Now in my head I just remembered that sigma is not sideways, so sigma is not equal to sideways. That's the way that I put it in my head. So I always know that sigma is head-on overlap of orbitals, but the pi bonds are sideways overlap, and specifically of p orbitals. If you forget that p, then you've kicked the 3 points away. So you should be able to draw your sigmas in your diagram on the top of page 146. You should be able to draw your pi's in the what would be the green above and below. And in terms of the description, you have two things: how they look, so this is the how they look, and then you have the definition of them, and the definition is really what you want. Okay, so you have it for both. So this is how they look down here, and this is the definition in the red box. Okay, and no sideways in sigma is the hint. So the two S's do not go together in this instance. Now there is an awful lot more going on, but as I say, in Leaving Cert Chemistry we don't touch it. All you have to think about is that bonds are where your electrons are going to be found, guaranteed. And these pi bonds are, because they're above and below the plane of your sigma bonds, it means that they're available to get involved. So this is why something like ethene or molecules that have double and triple bonds can be very, very reactive. If you just want to make a note for yourself on page 46 somewhere, yeah, so we've said it. Please note these bonds are areas of high electron density or regions of high electron densities. Your pi bonds are exposed and they are vulnerable to attack. So the rule would be double and triple bond molecules are, if you have this or you have this, then you are going to be very reactive. Okay, whereas just regular carbon-carbon single bonds, not so much. Now in terms of ethene, so if you have to describe the bonding, it's, while it is a double bond, it's not two single bonds, it's composed of a sigma and a pi. So you can use the Greek words for them. They're sigma and a pi bond. And we've just explained why. So nitrogen is now a triple bond. So that is not three single bonds. It is going to be one sigma and it is going to be 2 pi. So in reality, for that nitrogen, this is our sigma along the plane. There will be a pi bond, and they will actually be a second pi bond above and below this. In reality, the HH in hydrogen is just one sigma bond because it is a single bond, so it is a sigma bond. So in your notes now you have done nitrogen, you have oxygen in there, you should be able to do, and there's 2 questions at the very bottom for you. Okay, so we're going to leave that there for now. So for this next part, we are going to look at bond shape and bond angle. And there are 5 bond shapes and 5 bond shapes and their corresponding bond angles that you are going to have to know for Leaving Cert Chemistry. This comes under a thing called VSEPR, Valence Shell Electron Pair Repulsion Theory. And this is a really important rule. And by the end of this, you will understand what this rule means, and you have to be able to recognize, when you look at a molecule, what is present in terms of what are called lone pairs and bonding pairs, and then therefore use that to explain why this molecule has that particular shape and that particular bond angle. So to be able to do that, we have to go and understand what a bonding pair and what a lone pair are. So bonding pairs do what they say on the tin. So this is a molecule of methane, CH4, and you can clearly see from its dot and cross that there are 4 covalent bonds in here. So a bonding pair is the shared pair of electrons which form the covalent bond. So CH4, we are roughly on page 147, but CH4 in our example has 4 CH bonds and it has 4 bonding pairs. And in a minute, when we do look at shapes of molecules, 4 bonding pairs is very specific shape of and very specific bond angle. A lone pair, then, you can see in this diagram here, this is ammonia, NH3, and this is now different up here. So a lone pair are pairs of electrons that aren't involved in bonding. They're still on your outer shell, and they have a big influence on bond shape and bond angle. So here we had 3 NH bonds, so we have 3 bonding pairs. But more importantly, we have 1 lone pair. And you have to think about lone pairs in the terms of these guys are bullies. They really don't like the bonding pairs and they actually push them away. So that's going to change our bond angle and our shape of our molecule overall. And if you have 2 sets of lone pairs, well, they're going to even bully the bonding pairs even more and push them way down here, and they're going to change their bond angle and make it much smaller. So you're going to go and play with this PhET simulation. I have put it for you on Teams. We're going to start with first. You are going to find out for me. We are going to do XEF2. You're going to find out the shape and the bond angle of this. I'm going to pick something that we are not going to do. So I'm going to pick PCl5, and you can go real or model. Doesn't matter. So real, this is the atoms, and model is just a model of something that has the same shape. You're going to make sure you've clicked on molecular geometry, and you're going to make sure you've clicked on show the bond angles, and you can rotate these guys around and you can see how they orientate themselves. We don't do have to know the shape of PCl5, so the ones that you are going to do for me to start with is I'll write them down on our screen. You're going to do XEF2. You're going to make sure you have ticked molecular geometry, and you're going to make sure you have ticked bond angle. That's your first thing, and you are going to find out the shape and the bond angle for XEF2. You are going to find it out for BF3. You are going to find it out for CH4, and then you are going to look for me NH3, and finally H2O. So you can see them all here in the drop down. So you're going to find the shape and the bond angle, and what you are going to do for me is I'm going to go back to our presentation. Wrong place. So you are going to have a look on page 147. You have this kind of L shape, and I've drawn it specifically for this, and I'm not sure whether or not I've drawn molecules in there, but you're going to do your little diagram in that. And on page 148, you are going to be able to again draw your molecule, so your stick and ball. So XEF2 should look like this, and you'll do the same for BF3, and you'll do the same for CH4, NH3 and H2O in your diagram, and you will be able to tell me for each of those molecule bond pairs and lone pairs. You will also be able to tell me a shape and a bond angle, and then you're going to come back on to me at 9:40, and we are going to see, can we finish this. See you soon.